Hi everybody. I'm going to do a test run for our first Monday experiment, which will be mass and spring systems. And I'm going to try and do it at the pace that I think that will go in class to see if everything fits in the right amount of time. And I'll probably post this video afterwards. So mass and spring system. These are used a lot in computer graphics to simulate various types of materials. So they're used to simulate cloth or other kinds of deformable objects. And the idea is we'll have a class representing a point mass, so it's just like a little mass, and then we'll connect all of the masses with springs, and springs, when you compress them, will exert a force that tries to get them back to their resting state, or if you stretch them, again, it'll exert a force that will try and contract them again. So we're going to use a mathematical model for classical springs called Hooke's law. Now what Hooke's law says is that the spring has a resting length, and the force that it exerts if you compress it or expand it is going to be proportional to whatever that displacement is. So if you displace it, and then K is the proportionality constant. This is sometimes called the spring constant, and you can think about it as like the stiffness of the spring. So if K is a really large number, that means that even a small displacement will result in a large force. So that's a very stiff spring. A very kind of loose spring would be a small K value, so that way you could have a pretty large displacement and still not a huge amount of force to try and restore it to its resting length. Okay, so just another little reminder of some of the basic physics. If I have a point mass and I want to know what's going to control its motion, we're going to use basic Newton's laws of motion. So force equals mass times acceleration. So if I want to know how is this particular mass right here going to change in the next time step, what I'll do is I'll add up all the forces that are getting exerted on it. And right now that's just the forces of the springs. Although later on we might want to add other forces like gravity, or like when objects hit each other, there might be a collision force. So we'll add up all the forces on our object, and then we'll divide by the mass of the object, because if you imagine dividing by mass on both sides of this equation, that'll give us acceleration. And if you think of sort of conceptually, what is acceleration? Acceleration tells us how fast the speed is changing with every time step. So if we have a constant speed, then we know that our thing isn't accelerating at all. If the speed is increasing over time, just conceptually, that makes sense that it would be a positive acceleration. If our speed is decreasing with time, again, it makes sense that that's a negative acceleration. So we'll have an update step where we'll say, take our current velocity, add in whatever our acceleration is, and that's the new velocity. And then we can do that same process again to update the position, because velocity just tells us how our position is changing with every time step. And it makes sense if you think about units. So velocity, you could think meters per second. Well, that's just telling us how far, meters, our position is changing with every time step, which we'll measure in seconds. So same thing, we'll take our current position, add in the velocity, and that gives us the new position. I'll say that, for professional kind of graphics packages where you're actually representing deformable objects with huge networks of masses and springs, you wouldn't actually do it this way. You would end up writing differential equations based on these same physics ideas, but you just write it in a different way, and then that would let you solve it in a very efficient way. Since we don't know calculus, we're not going to do any of that. But we can still do the basic idea with kind of a smaller system and just a little bit less computationally efficient. So that's the idea. We're going to have a class representing our masses, we'll have a class representing our springs, and we'll sort of connect the springs and the masses to each other, and then we'll have a physical system that updates itself once every time step using these kind of basic physics laws. All right, so let's talk about just a couple code things for a second. We're going to use a built-in class that processing has called p-vector. P-vector represents a vector, and if you don't know what vectors are, you can think of a vector like an arrow, except this is going to be an arrow in 2 dimensions. So if I have an arrow that's pointing right and up, you could think about the horizontal part of the arrow and the vertical part of the arrow, and that's the x component and the y component of the vector. So vectors are sort of the right tool to use for representing accelerations and velocities and even positions, because they very easily let us say like what direction is the acceleration happening in. That's the direction the arrow is facing. And then also how big an acceleration is it? And that corresponds to how long the arrow is, which makes intuitive sense. If you have a really long arrow pointing this way, you'd think, wow, it's going really fast in that direction. And that's kind of what vectors let you do. Okay, so if you want to look up the whole API for the vector class, it's here. We'll probably be using mult. Mult lets you multiply a vector by just an ordinary real number, which is sometimes called a scalar. And that's how we're going to make the vectors, like stretch them to be longer or shorter. Mag will return the magnitude of the vector, which is another way of saying how long is the arrow right now. Normalize will take the vector and it will squish it to be length 1. And you might think like, why would we want to do that? But that's helpful because if we have a vector if we have like an acceleration pointing in a particular direction, and we just want to know what direction is it pointing. We don't want to know sort of how fast or slow is the acceleration. If you normalize the vector, now you have length 1. And if you think about length 1, that's, if you multiply that by something, you're not changing the value. So you're not, it's not increasing or decreasing anything. It's just telling us the direction, not really the magnitude. Here's what I'm imagining for our API for the mass and spring classes for the moment, although this might change. So if I think like, what facts describe a mass? I've got position and acceleration and velocity. And then if I'm going to display them to the screen, I'll want a color and a radius. And then, of course, the mass, I actually have to say, like, what's the amount of the mass? And in terms of behaviors, in terms of methods, I'll want to be able to add a force to the mass. And that's going to happen every single time I have a spring connected to it. So for each spring, I'll say, hey, spring, please add your own force contribution to that particular mass. So we can sort of add a bunch of forces and they'll all kind of accumulate. And then we'll run update. And what update is supposed to do is it's supposed to take that current, it's supposed to take all those forces, which give us an acceleration. And using that acceleration, we'll change our own velocity, we'll change our own position, and then we'll reset the acceleration for the next time step so that we can sort of see what forces are accelerating us in this new time step. And then we'll have a draw method, which will draw the thing to the window. For springs, every spring will connect exactly 2 masses. So we'll have a mass object. We'll have 2 mass variables inside the spring. We need to know what the stiffness constant of the spring is, and we'll need to know what's the resting length of the spring. And other things we might want to know, I'm thinking like, what's the current displacement of the spring? So, is it being stretched or squished, and by how much? And then apply force to masses. So when a spring object runs this method, it will look at its own displacement, it'll look at its own stiffness, it will figure out what force to use based on those 2 things, and then it'll apply that force to the 2 masses using the add force method here. So that's kind of how I'm imagining everything will fit together. All right, let's go to IntelliJ and start doing it. Okay, so we're at 9 minutes. Here we are. I've made a mass spring system. So let's create our classes first. I'll have a class called main, and this is what I'll run everything from. And I'll say public static void main. And then I'm going to make a spring class. And, oh, the baby sounds upset. And now I'll have a, mass class. And I think I'm going to create a class for the whole system. So mass spring system. Okay. So let's start filling in some of the bits that we need. So for mass, what did I say I wanted? Okay, all right, let's do this. So private p vector, and then we'll have a position, an acceleration, or a velocity, and an acceleration. Okay, so p vector is not recognized because I said this is part of the processing graphics package. So we actually have to import everything associated with that. So we have to use their core.jar library. So let's go to File and Project Settings. Where's that? Oh, Project Structure right here. And we'll go to Libraries, and we'll press the green button to add a new library. And now we've got to find where is core.jar. So for my machine, where in fact did I put it? Okay, so I've got a lib folder here. I think in yours it's in the C, on the lab computers, it's in the C drive, and there's a folder called processing libs, or possibly just libs. We're going to use version 2 of the processing jar. The most recent version is version 3, and there's a couple of differences that I don't want to use here. So if you've downloaded your own, either you got to figure out how to use it, or go back and from the website you can download an older version of processing, and any of the version 2 ones should work. So for mine it's called Core V2. Cool. I'll say OK. And now I can click here and hit Alt-Enter and say Import Class, and now it's there. All right, great. So what else did I say I wanted? So I've got those things. I'll have private float mass. I'll have private int color. I'll have private float radius. And I think maybe that was everything that I said. So I forget how to generate constructors. So I did Control-Shift-A. I'm going to type constructor. Okay, so I'm going to construct it just with, let's do this. So at a minimum, we're going to need the mass. Let's do a radius and a color. We'll start with velocity and acceleration both 0, but we'll need a position. But let's not force the position to be a p-vector. So let's just construct it with that much. And then the position we'll add in as an x and a y coordinate. And then in here we'll say this dot position equals new p-vector xy. Because I think it's nice, whoever's using our mass class, I don't want them to have to mess around with p-vectors. Like from their perspective, they just want to tell us where's the location of the mass in x and y. And the p-vector is how we're representing it, because it's convenient for us, but we don't want to impose that burden on the user of this class. All right, so there's the mass constructor. Let's do some of our methods. What else did I say I wanted? So public void, so public void, I said I wanted add force, p-vector force. Well, all that talk about not imposing p-vectors. Well, let me introduce an idea to you. So, all right, so let's do this first, and then I'll introduce an idea to you. So if we're going to add in a force, here's what we want to do. We want to take our current acceleration, and we're going to add in a new p-vector. But I don't want to just add in the force like this, because remember, this is an acceleration. And acceleration is force divided by mass. So first I'm going to say force dot div for divide, and then I'm going to divide by this dot mass. I'm just have this there to be explicit about it is our mass. So I'm dividing the incoming force by the mass, and then I'm taking that force and I'm adding it into our own acceleration. Okay, so let's do something called method overloading. So maybe I want to give whoever's using this class a way of adding a force without making their own p-vector. So I could add another method, public void add force. See how it's exactly the same so far, except now I'll have a float x, float y for the xy components of the force. So I want this to do the exact same thing. And if I wanted to, I could do whatever calculations I've done in here. But instead, that would be repeating myself. I already have this nice method that will add in a force if only I had a p vector. So what I'll do in this class is I'll make a temporary p vector called f, and so new p vector. I'll give it the xy, that's the input here. And now that I've created a p vector out of those components, now I can use my own method that I already have. So I'll say this dot add force, and then I'll give it this force vector. So this is pretty common. So first of all, this is called method overloading. What that means is that I have two different methods that do the same thing. They have the same name, but they give options as to what inputs does somebody have to have in order to use them. So it's just like giving somebody options. Like you could add force with a p vector, or you could add a force with an xy component. And because they're supposed to be doing the same thing, it's pretty common to have one of them run the other version. So that way, if you want to change how it works, you only really have to change one of them, because that's where all the logic is located. All right, so that's add force. What else did I want to do? Wow. Oh yeah, I wanted to do update. So public void update. And what I said about update was I wanted to use the acceleration to update the velocity, and the velocity to update the position. So I'll say velocity dot add acceleration, and then I'll say position dot add velocity, and then I'll say acceleration dot, is there a clear? No, acceleration dot, can I set it to something? Let's do set it to 0, 0. So that'll like reset acceleration. Let's think, does this do everything we want it to do? Yeah, that makes sense. Cool. Let's pause for a second. So I guess the last thing we wanted to do here was draw it. So public void draw, and we're going to take a p-applet as an input. P-applet you can think of as meaning like graphics window. So I'll call it window. You have to import p-applet, so you can click on it, Alt-Enter, import class. And there's a command called ellipse. So I can say window.ellipse, and that's telling the window that I want to draw an ellipse there. And it takes 4 parameters, which are the center of the ellipse and then the width and the height of the ellipse. So the center of our ellipse is going to be at position.x, position.y. It's like our own xy. And then the width and the height are going to be radius times 2 and radius times 2. Because we're going to represent this as a circle rather than an oval. So the width and the height of the circle will be twice the radius. I think that's everything. Well, so let's use the right color. So window.fill, if I do this right before ellipse, I'll make sure that I'm filling it with the right color. And I'll just use color here. Okay. Let's do this. Let's overload the constructor as well. So, because I'm thinking I don't want to force people to figure out how to use colors. So I just copied my constructor. I'm pasting it. So I'm making another version of the constructor, but now without color. And in that case, I'm going to say this.color equals default color. And default color I've made in all caps, and I'll hit Alt-Enter and say create a constant. So here it is at the top. So I'm going to create a default color, and let's just make the default color be black. So 0 will be black. Okay, so far so good. Let's test it a little bit. So let's go to main. I'm going to delete public static void main. So we're going to make a processing applet. So here's sort of the template for how you do that. You say public class main extends p-applet. Remember, p-applet means like graphics window. You got to import it again. And now I'll say public void setup, and we'll make the size of our window be 600 pixels by 600 pixels. And then we'll say public void draw. And draw is so setup runs exactly once right at the start when you run your program. So as the name suggests, it's for setting things up. Draw runs in a loop. I think about 25 or 30 times a second, but kind of dependent on your processor. Let's say background 255. So this will wipe screen with white. And let's just test what we've got so far. So we'll create a new mass and just make sure that we can see it. So here I'll say mass M, and then here in setup I'll say M equals new mass. And I've already forgotten what the parameters are. Is IntelliJ going to tell me? Okay, right. So I'll give it 1 for the mass. I'll leave out the color. We'll let it be the default color. The radius, let's make it be like 20 maybe. And then X and Y, I'll have it be located right in the center of the screen, 300, 300. Okay, let's just make sure that it can draw okay. So I'll say mass.draw. And remember, draw is expecting a graphics window as an input. And look, our program right here, main, we are a graphics window because we're extending the definition of a graphics window. So if I use the keyword this, meaning the current executing object, and I pass that as an input to draw, I'm saying kind of bundle up the current graphics window that is this program and hand it to this mass object so that way the mass object can take that window and tell the window, here's what you need to draw on yourself in order to draw me. All right, let's go back. So that looks pretty good. So I'm ready to run it. And it's running maybe. Nope. Why has this failed? Usage papplet, blah, blah. So maybe if can I tell it to run as an applet? No, of course not. Okay. All right, so we need one more thing. Down here, let's go back and do public static void main. We'll say papplet.main, and then we'll give it the name of our class right now, which is main. If you've created yours inside, we're using the default package. If you've created a package that yours is inside of, you'll know that because at the very top it'll say package and then some things. So if you're inside a package, you actually have to type your package name here. So if my package was FHS, I'd need to say fhs.main. All right, let's try and run it again. Cool. Okay, so there's our mass, and it's not doing anything because it's just sitting there. Let's go ahead and have it move. So inside the draw loop, which is looping a bunch of times a second, I'll say m.add force. So let's add a rightward force. That's like a force of, I don't know, 2 and then 0. Or let's do 1.1 f. F means float. Okay, so it should be going right and kind of uppish. And cool, we get null pointer. All right, time to debug. Oh, I know why too. Okay, so let's click here, which is where it's happening. Okay, so the null pointer is happening on this line. And what null pointer means is that we have a method that is supposed to be run by an object, whatever object is inside this variable, but actually there's nothing inside this variable, it's null. And the reason why is because I forgot to initialize these p vectors. We've got position, that part's okay. But let's say this dot velocity equals new p vector 0, 0, and then this dot acceleration equals new p vector 0, 0. Okay, let's try it again. Okay, still having a problem. So let's go here and see what the issue is. Still doesn't like, Is that really true though? Oh, ha. Okay, so look what happened. So I initialize them in this constructor, but this isn't the constructor I ran. So this is happening to me because I used bad practice. Remember what I was saying before about overloading methods, where like one of them should call the other one? Well, I just copy and pasted. That's repeated code. And this is exactly why you don't want to have repeated code. It's because if you decide to change it, you change it in one spot, you forget to change it in the other spot, and that's where the bug came from. So what I'm actually going to do here is I'm going to have this constructor run the other constructor using the default color. So counterintuitively, the word this, but used as a method, is how you run the other constructor. So I'm going to pass my mass, and then the next thing it's expecting is color. So I'm going to use the default color. And then I'm going to pass in my own radius and the x and the y. Okay, great. So hopefully this time, everybody. All right, cool. Is it moving? No. All right. This is, you'll notice though, so there's a bunch of bugs and you might be thinking this is lame. But this is another aspect of good practice. I stopped here to test just as much as I'd written with mass on purpose for exactly this reason. Like, we could have gone on and kept trying to write Spring, but I thought, let's just debug this part first, because it's going to be easier to debug when there's less code. If I programmed a bunch of other stuff and then went to debug it, it would be a lot harder to figure out. All right, well, I don't see it moving, so I'm going to display some values to try and figure out what's going on. So here we're inside mass. I think that when we say add force, I should be changing the acceleration, and then update should be updating the velocity and then the position, right? So let's check to see if that's actually happening. So I'm going to s out for system.out.println, and I'm going to print the velocity, but let's actually include the word velocity first so I know what's going on. And then let's say s out position, and let's print the position. So now we'll be able to see, like, is it actually moving or not? And then I'll just have an empty s out here. Or like, let's display some dashes. Okay, so let's run it and see if the output is what we're expecting. So I'm not seeing anything get displayed, and I know why. Wow, this is a really bad session. All right, guess what, guys? We are drawing it. We're adding the force. But what are we not doing? What we're actually not doing is updating it. Forgot my own process. All right, so we add the force. Now we update everything. Now we draw. Cool. Okay, this time for sure. Famous last words. Oh, there we go. All right, so it shot away. So let's make all of these little, I'm going to divide all these by 10. So like 0.1f. Okay, let's run it again, see what it looks like. Okay, cool. So there, it's accelerating off the screen. I'm going to remove these print statements because the printing actually slows everything else way, way down. All right. Great. Okay, so far so good. That seems to be working. Oh, let's do something fun. So instead of adding a constant force, I'm going to add a force that is toward the mouse. So let's do this. P vector position equals m dot get position. So I'm just going to create, so I'm going to import p vector, boop, boop. I'm going to create the get position method where I am just going to return position. And now, so in processing, the variable mouse x represents the mouse's current x coordinate. So if I want to go towards the mouse, let's do position.x minus mouse x, and then position.y minus mouse y. But we're going to want to divide it by something really big. So let's divide it by like 500.0 flipped. That might be too big, but we'll see. Oh, I am, of course, I'm accelerating it away from the mouse. Let's try this again. So I'm going to put negative signs here. Cool. Well, this is entertaining already. All right. So let's think about springs now. Okay, so what did I want to do for spring? Let me check that page that I'd made. Right, so spring connects two masses, has a k and a resting length. Okay, so private mass m1, m2, private float k value. So this is spring stiffness constant. Let's have a color. We could have a line thickness, but I guess let's not do that right now. Right, resting length. Here, I'm going to group that together with the K. So private float resting length. All right, and let's make a constructor. So I hit Control-Shift-A. I'm typing the word constructor. Cool. So I'm going to construct it with the two masses and the K, and let's not construct it with the resting length, because I think we're going to have it be like, let's make the resting length be whatever, like when you first create it, it's connecting these two masses. Let's make that be its resting length. So however it starts, that's like, because remember the masses already have locations on the screen. So we'll say this dot resting length equals m1 distance to m2, which doesn't exist yet, but let's make it, because that seems like a convenient thing to want to do. I'm just going to call this one other. So my favorite way of calculating distance is we'll have a delta x, which is the difference between this x. Oh, except we don't have x's and y's, right? We've got position. Ooh, I bet p vector already has a built-in one. Let's do this. So this dot position dot dist. Great. So it's got a built-in distance between p vectors. So let's say other dot position. Cool. Okay, so I'm making an assumption about what this does. So to do this might not work, or what do I want to say? Does dist really compute Euclidean distance? I don't know. I guess we'll find out. So, all right, we better do it right now because it might not, and that would make us sad. So let's do processing p vector dist, calculate the distance between 2 points. Sweet, that is what we want to do. Okay, now I feel more confident. No, I don't want to sign into anything, please, thank you. Cool. So we've made our spring constructor, we're connecting two masses, we got the k value, distance, okay. So what else did I say I wanted to do with springs? Right, get length displacement, apply force to masses, and draw. So public float get length displacement. So the displacement is the difference between its current, the distance between its current masses, because those masses are the endpoints, and whatever its resting length was. So we're going to return m1.distance to m2. Because remember, m1 and I know that's the same as how we set resting length originally, but remember, m1 and m2 are going to be moving around. So later on in the program, when we say, hey, what's our displacement right now? Like, are we squished? Are we stretched? Then we'll say, hey, masses, calculate the distance between yourselves now, and let's compare that to whatever you said your distances were originally. So subtract resting length. Cool. So that should probably work. And now apply force to mass. So public void apply force to masses. Okay, so this requires a little bit of thinking. So I want to say like m1.add force, and I'll need to have like some force. But I got to figure out like what direction is this force in, and how big a force is it? So let's do this. I'll say p vector f equals new, or let's maybe make a p vector that's, so let's think. Let's get the direction right first. So let's get the direction from mass 1 to mass 2. So like that's an arrow that's pointing from 1 to 2. So m1 dot position dot can we subtract? But that's not going to give us, let's do this, p vector dot subtract. Great. Let me look up how p vector works again. Okay, so this is the part that's going to go more smoothly in class. P vector processing. Sure. Subtract. Is this going to give me the static version though? Where's the static version? Okay, the version of the method that subtracts two vectors is static and returns a p vector. The other acts directly on the vector. So if we use the static version, we're not going to mess up the vectors we have. So let's do m2 and m1. What's it actually expecting? Oh, m2 dot get position and m1 or m2 dot get position. Okay, so that's now in some position. So now I've got a vector from mass. So wait, I did 1 minus 2. So this is now pointing from 2 to 1. So it's pointing in the direction maybe that we want, but now we have to scale it by whatever the actual force is. So let's do this. Let's say f dot normalize. So now we keep the direction, but we've made it length 1. And so now we can say let's multiply it by the force. And the force is going to be get length displacement times k. Should it be negative k? Should it be positive k? We could have thought about this harder. Like I would have to draw it on a piece of paper because I can't visualize it in my head because I'm not good at that. But instead, I'm just going to sort of test it and see if it seems to be applying a force in the wrong direction. And if it is, I'll just reverse it. So we're adding now that force to m1. And let's do this. So I want to add the opposite force to m2. F dot mult or p vector dot mult, f and then -1. So if I multiply by -1, that's now reversed the direction. Okay, cool. Well, I expect this will probably have some bugs in it, but let's give it a go. Apply force to masses. Okay, so in order to test it, let's actually do this. Instead of setting the resting length to be whatever it was originally, let's set it to be like 90%. So what that means is that when you create a spring connected to two masses, it's already being stretched by a little bit. So we should see them contract toward each other. Okay, so here we are back in main. So I've got m. Let's make m2. So I'm going to change m to be, all right, so mass 1, radius 20, but let's put it at a location of 200 in the x. Let's have m2 be a new mass, whose mass is 1, radius 20, but we'll make this one be 400 and 300. So they're kind of horizontally situated with respect to each other. And now let's make a spring. So up here I'll say spring s. S equals new spring. Spring. And I will give it a mass 1 and a mass 2 and a spring constant, which I don't know what I'll make it, 0.5f. I have no idea if that's too big or too small. We'll see. Let's make it like kind of small. Let's make it like 0.2. Okay. So what am I trying to do? All right, so let's delete this. Let's delete this. I don't want to update. Oh, I do want to do that. You know what? Let's think. That's always a good idea before typing. So I've got my two masses. I've got my spring. So springs don't require any updating. They do. So s dot apply force to masses. We want to do that every time. And then m dot, so we don't need to add force because the spring's doing that for us now, remember? So instead, like, we do want to update them both though. So m update and m2 update. Let's say m dot draw this and m2 dot draw this. Ooh, let's real quick say s dot draw. Because I want to see the spring also. So let's create that method in spring. Here it is. I don't want main, I want papplet, which we'll call window. And we'll import it. Okay. So what do I want to do? I want to say fill with, I'm running out of time, so let's just say fill 0. Or we don't want to fill it. Stroke, so because it's going to be a line, so let's draw a line first. So window.line. You take an x1, y1, x2, y2. So we want mass1.position.x, mass1.position.y, and then mass2.position.x, and mass2.position.y. Okay, but it doesn't know what position is because using good practice, I should say get position. .x, and then same thing here, .get position, and then here I should say .get position. Perhaps I should have done this in a shorter way. .get position. Okay, cool. So that's going to draw a line. That's probably going to work. Okay, let's try it. Okay. So it happened really quickly, but they shot away from each other, which means that I am doing this in the wrong direction. So, so let's multiply it by -k here. Okay, let's try that again. There we go. Good spring. So that's kind of what we expect to see. Let's make the spring stiff. Let's play around with it a bit. So let's make the spring stiffness like a little bit less. Let's make it 0.05 and see what that looks like. That looks a little bit better. Let's make it 0.01 even. Okay. Oh, that's very pleasing. Okay. And now what do I want it to do? Let's make one of them be 10 times more massive than the other. So M2 is now 10 times more massive. And that makes sense. Like this one isn't moving very much because it's not affected as much by the force. That's cool. Okay, and so now let's also do this. Oh, so much fun. So M2, so every time, let's say M2 dot add force. And so let's do that same thing. Let's say mouse x minus M2 dot get position dot x and mouse y minus M2 dot get position dot y. And remember, we were dividing that by 500. And divide it by 500. Or let's divide it by 800 because I don't want this to be a huge amount of force. Okay, so now the really massive one is going to sort of follow our mouse, and the other one is going to bounce around. Can I slingshot it? Sort of. Okay, well, so we've got sort of a system. We're not doing anything like super cool yet. Well, I don't know. I think this is pretty super cool. Yeah, take it all back. This is sweet. This is super cool. And we are at 45 minutes, so I'm going to stop now. Yay!